Kinetic molecular theory is the simplest model for the behavior of gases. The idea here is that we think of the gases as being a collection of particles, those could be molecules or atoms, that are in constant motion. So here we have an illustration. These little particles are zinging around until they hit something, and then they bounce off. So the first idea in this theory is that the size of a particle is negligibly small. So we're assuming that the gas particles occupy no volume, even though they do have mass. Of course they have volume, but the volume is so small compared to the overall volume of a gas that we can ignore it, right? So let's say you're seeing, well, maybe you're at the doctor and you're on the scale and you're going to see how much you weigh. And then someone hands you a penny. Is that going to affect what the scale says? No, because that is so small in mass compared to your whole body that it's not even going to move the scale, right? So that's the way it is with the volume of these particles. There's just so much empty space. At STP, if you had an argon atom that was the size of a golf ball, its nearest neighbor would be 4 feet away. That's a lot of empty space. Come on. Second idea is the average kinetic energy of the gas particles is directly proportional to the temperature in kelvins. If you raise the temperature of the gas, you raise the average speed of the particles. They are not all going the same speed, but the temperature is a measure of the average kinetic energy. Third idea, the collision of one particle with another or with the walls of the container or anything else is completely elastic. And what we mean by that is when the particle collides, it just bounces off and it doesn't lose any energy. I can't think of a really great example of an elastic collision with, things that are big enough to see. Billiard balls are fairly elastic in their collisions. They'll bounce off of each other, as opposed to, say, lumps of clay, which are just going to roll into each other and go home, right? And they're not going to bounce off at all. So elastic collisions. Well, yeah, this is why I had these ideas in my mind. So elastic collision would be like these billiard balls, and they come and they bump into each other and they bounce off, and they're going pretty much the same speed as they were before. Whereas if you roll lumps of clay to each other, they just stop, right? All their energy is lost as heat. So we can use the kinetic molecular theory to explain a lot of things. We can explain the idea of pressure. So those gas particles are constantly moving. They're going to hit the sides of the container with a force. The result of lots and lots, and we're talking gazillions, right, of gas particles in a sample exerting forces on the surrounding surface is going to result in a constant pressure. It's the force divided by the area. Any questions about that? Kinetic molecular theory explains Boyle's law. The volume of a gas is inversely proportional to the pressure. If you decrease the volume of a gas, then you're forcing the molecules into a smaller space. So in that smaller space, more molecules are going to be colliding with the container, so the pressure will be larger. Charles' law, volume is proportional to temperature. When we increase the temperature of a gas, the average speed and average kinetic energy increases. So now there's going to be more collisions, and the collisions are going to have more force. So in order to have a constant pressure, we must allow the gas to expand to maintain the constant pressure. that spreads the collisions out over a larger surface area. Avogadros Avogadros Law. The volume of a gas is directly proportional to the number of gas molecules. If you increase the number of gas molecules, there'll be more of them hitting the wall, and again, if we want to keep the pressure constant, the volume's going to have to increase. Dalton's law. Total pressure of a gas mixture is the sum of the partial pressures. So the particles have negligible size, so it doesn't matter that one is oxygen and one is nitrogen or something else. The size of the particles doesn't matter. They're all going to behave the same. They are going to have the same average kinetic energy. Now, they're not going to have the same speed, but the kinetic energy is what impacts the walls and causes the pressure. So average kinetic energy is the same, so then the total pressure of collisions is the same as if they were all a single kind of gas. There is, if you're interested, a derivation in the book showing how kinetic molecular theory leads to the ideal gas law. What's very important about this theory is it predicts behavior that's consistent with observations and measurements of gases. Scientific theory is the most powerful kind of scientific knowledge. This model doesn't work under all conditions, but even where it breaks down, it gives us information. Helps us to understand gases by looking at what are those conditions where it breaks down. So the average kinetic energy of gas molecules is 1/2 times the mass times the velocity squared. So if we have gas particles with different masses, the only way they can have the same average kinetic energy is if they have different velocities. So in a gas mixture, we're going to see that lighter particles are going to travel faster on average than heavier ones. And, I had 4 boys play high school football. So I've seen a lot of football games. So this makes me think of running backs and guys on the D-line, right? So the guy on the D-line, he's a big guy, right? Does he run very fast? Probably not. And the running back is a smaller guy, usually kind of slim, and he can run really fast, right? So lighter particles travel faster, heavy particles travel slower. When we're talking about the average velocity, we're actually using something called the root mean square velocity, URMS. It's just a special kind of average. It's very close to the average velocity, and there's very good reasons that they use it, and we're not going into that. So this is a useful equation. The root mean square velocity of a collection of gas particles will be equal to the square root of 3 times RT over the molar mass. It's important to note here that the molar mass needs to be in kilograms per mole. And that is because a joule is I'm blanking on it now. The kilogram is the base unit in the SI system, and units like joules are actually composed of other units, and the units work out if you do it in kilograms, and otherwise they do not. So we see that lighter particles, like hydrogen, have higher average velocities, and heavier particles have lower average velocities. They travel more slowly. The other thing that's interesting is that the lighter particles have broader distributions. So we don't have this peak that just moves over. It moves over, but it also flattens and broadens out. So there's a lot of variation in the speed of the hydrogen molecules. If we look at the velocity as we change the temperature, 273 Kelvin, 1,000, and 2,000, we see that the average velocity is increasing, but we also see that the distribution is spreading out or shifting. So here's a for practice question. Calculate the root mean square velocity of gaseous xenon atoms at 25 degrees Celsius. You do not need to memorize this equation. Just need to know how to use it. That is the equation for the root mean square velocity. So here we've got 25 degrees Celsius. So the temperature is 25 Celsius. And what do we think? Does that need to be in kelvins? Yeah. So plus 273 gets us 298 Kelvin. We've got R in that equation, 0.08206 liter atmospheres per mole Kelvin. And then we've got the molar mass in kilograms per mole. So xenon is 131.3 grams per mole. So I need to convert this to kilograms. And kilo stands for 10 to the 3. So I'm going to end up with 0.1313 kilograms per mole. And now we can plug these units, the numbers and the units into this equation. So the root mean square velocity is going to be 3 times R times the temperature divided by the molar mass in kilograms per mole, and needed to be the square root of the whole thing. On my calculator, I put the square root thing in first, and then I do the stuff underneath. Other calculators, you might need to do the multiplication and division and then take the square root.
So the size of the M is messed up because capital M is usually low M.
Yeah, so I tried to draw it here. It's kind of like an italic capital M.
Yeah, I seen that leg, it came out a little.
Yeah, whereas molarity, I usually underline. There's a lot of M's. There's milli and there's meter, right? And then there's micro. So, and mega. So, just not enough symbols, I guess. So I'm getting an answer of 23.6. Now, what happens with the units? Well, in here, I've got my kelvins canceling. And then let's look at what happens here. So I've got liter atmospheres. Let's just do all of it down here. Times mole, times Kelvin. And then I multiplied by Kelvin. And if I divide by this fraction, that's the same as multiplying by the inverse of the fraction. So the moles cancel and the kelvins cancel, and I am left with liters times atmospheres divided by kilograms. Yes, I see where I went wrong. Okay. This is a different version of R. With units of joules per mole Kelvin, and we use that one when we're going to do things with joules. Because what happened here is I got to atmospheres and I realized, dang, this is wrong. There's a conversion between liter atmospheres and joules, but we haven't come to that yet. Okay. So, let's fix this. .314 joules per mole Kelvin. So I have to do the calculation again. So now I'm getting 237.9. Okay. So back to our unit simplification problem over here. Now I've got joules divided by kilogram. This was given because I always forget what this is, and I don't expect you to remember that either. A joule is a kilogram times a meter squared divided by a second squared. So that means that what I have over here now is I have a kilogram times meter squared per second squared divided by kilograms. The kilograms cancel out, and all of this we're still under the square root. So this is going to end up being the square root of meters squared per second squared, or meters per second. And that's why it has to be in kilograms. That was ugly. Sorry about that. We will encounter this R in other places as well. But we're only going to see these two. Only the two. And I will give them to you with their units on the useful information page, right? Yeah. Okay, let's look at this one. No calculations. Which sample of an ideal gas has the greatest pressure? Assume that the mass of each particle is proportional to its size, and that all the gas samples are at the same temperature. And we're supposed to be able to see that the volumes are the same. So this one has big particles, and these two have small particles. And it looks like this one has more particles, right? 1, 2, 3, 4, 5, 6, 7. Also 7, more than 7. So which one is going to have the largest pressure? C. It's the number of particles that affects the pressure, not how big they are.